All right, we're starting a new unit today called heat. It's the first part of the thermodynamics unit. We'll have heat as the first part, thermodynamics as the second. They're all part of the same unit. And we'll start off with first talking about what heat is. And we'll talk about heat as energy transfer. Number one. So heat always flows from warm to less warm. If you ever open the door on a cold day and you're like, bruh, close that door, you're letting all the cold in. That doesn't make sense because heat is just energy. It's being transferred. So energy always flows from high concentration to low. That's warm to less warm. That's why I didn't say hot to cold. Cold is the absence of any energy. How do we represent heat mathematically? We do that with a Q. So Q is the variable for heat. And let's look at a couple different units of heat. The first one we have is the calorie. You can tell from the spelling, very British. So cal is the way, you may be thinking, oh, I know calories, that's food calories. No, food calories are actually kilocalories, so it's 1,000 times bigger than this. But it is the energy to raise 1 gram of water by 1 degree Celsius. Next up, kilocal. This is what I was talking about here, which is just going to be this guy times 1,000. So calorie times 1,000 gives us the kilocalorie. These are the food calories we have, so we can write food calorie. All right. The next one we have is the British thermal unit. You may have seen BTUs on a grill. Basically what this one measures, it's the English version of, like the imperial unit version of the calorie. So it is the energy to raise 1 pound of water by 1 degree Fahrenheit. Very American feel to it. We also have the therm, which is just equal to 10 to the 5th BTUs. And finally, where would we be talking about energy without joules? And for these ones all here, well, again, joule represented by J. I'll just set up the equivalence factor in case you ever need to do a conversion here. And there you have our units of energy for heat. So heat always involves a transfer of energy. Heat involves energy transfer. And so because of that, we can compare it to heat. Can be compared to heat. So let's do a little, sorry, not to heat, to work. There we go. So let's do a little work review. All right, with a work review, here we go, all of our work-related formulas. I'll get a little separation here. Work is equal to force times distance times cosine theta, which just basically means that it is the perpendicular component of your force times the distance that you cover. Additionally, we have that work is equal to your change in kinetic energy if you slow down or speed something up, or it's your change in potential energy if you're talking about lifting something up, pushing something down. When we talk about work, W is, this W that we represent here is work done on the system. This will become important in this unit, but especially when we start doing thermodynamic systems. This is work done on the system. So if the system is doing work, it would be negative. Does that make sense? There we go. And the unit for work, the unit is joules. There's our work review. Let's do a quick practice problem with it to see if you know how to use these units correctly. Let's say I ate a whole pizza. This is something I do on Saturdays. I tend to just put in a frozen pizza, eat the whole thing by myself. So let's say that I eat a 1588 calorie pizza. Remember, food calories are different than actual calories. So let's say I ate it says 1588 calories on the box if I eat the whole thing. I want to know what height do I need to walk to so I can burn the calories off? So in this one, we're going to have to do some type of energy change. I'll let you guys take a second, try and figure it out. I'll come back, give a hint, pause it again if you feel good after that, and then after that pause, I'll come out and show you how I did it. So your hint is that the amount of work that you need to do is going to be equal to the change in potential energy that you have. I have to do a certain amount of energy. I'm burning those calories off so that I can get my potential energy, the amount of height change difference. It's all going into lifting me up. And we're back. For me, I am approximately 66 kilograms. For my change in potential energy, that's going to be MGH. Work is over here. I know work, I need to burn off 1588 calories. So first thing I want to do is get everything in joules, since this is going to be calculating in joules. We'll do 1588 kilocalories. And from what I had before, a kilocalorie, I have 0.252, and for joules, I have 1056. When I plug that in, I find out that it's approximately 6.65 times 10 to the 6th joules, which I will promptly come over here and write down. 6 joules. Like I said earlier, I'm about 66 kilograms. For you guys, it's going to be slightly different. We use 10 for gravity, and we solve for height. When we plug that in, we get that our height is approximately 10,000 meters, or 10 kilometers up. That's a lot of energy. That makes you realize how much energy is actually stored in heat in your body. Because almost all of your calories get burnt off just by you thermoregulating, keeping your body at a temperature where the chemical reactions in your cell are most efficient. So now that we've got that, we're going to move on and talk about internal energy, which is also known as thermal energy.